My name is Dave Thompson, and on behalf of OlySoft, I'd like to welcome you to the first in a series of videos we'll be producing as a community outreach educational effort. We'll be teaching some pretty dry topics that might be considered out of reach by some people who otherwise have an interest. Electronics, programming, science, math, engineering. We'll be teaching these in what is hopefully a fun way that really sticks, because learning is fun if it's done right. Now, different people learn in different ways. Many different people means many different ways. Our goal at OlySoft is to use the open source technology available to everyone to help us teach basic STEM topics, to help spur understanding, collaboration, and then innovation. This is the open source way. This is our contribution to the fight to bridge the digital divide to all people. This first video is a test run showing a very simple project using an Arduino microcontroller, a single LED and resistor, and a few pieces of wire. This will solidify our tool chain and clear up what resources we might need to make this project a success as our ambitions and our videos get longer and more complicated. I hope you enjoy it. Alrighty then. Welcome. This is the OlySoft STEM series of educational videos. This is video 1. I call this the Blink video. In this video, we'll be going over a few things. We'll be introducing Arduino microcontrollers. Specifically, the Arduino Nano is what you'll see here, but I'll explain a little bit of what they do and how they do it. A microcontroller is a device that you can program to read values, write values, control things in your home, control things in a robot, control things in your car, read temperatures, humidity, resistance. It is what you would use if you're going to build something that does something. You can use a microcontroller to rapidly prototype a device, an invention, and long before you actually worry about getting an electrical engineer to produce a chip to do the same thing, to make it very, very, very cheap, you can use the Arduino microcontroller to work on things going forward. It duplicates so many things. It makes what's called the maker community possible, essentially. Things like the Arduino. Now, we're going to do some basic electrical concepts. This video will be using a resistor and an LED, along with, of course, the Arduino microcontroller. The resistor slows down, reduces the amount of electricity that passes through it. The LED produces light, but also only works in one direction. So we're going to be going over some things like that. Basic programming concepts. In order to do the blink, the Arduino must be programmed in order to turn on and off a switch that is built into it. Literally, to do that requires 5 lines of code and 1 variable assignment. And the variable assignment isn't even actually required. This video will set the stage for more videos to come. This really is a kind of a shakedown thing. I'm not sure what my entire tool chain will look like in software or in hardware. Going forward, these videos are going to become more complicated. There's a lot of things I want to get into, and this is going to be number 1, where I have difficulties I know I've got to work on, and we're going to have some fun. I don't script a lot of things. I'm just running this live, so if I flub up, please understand. Now, we're going to be doing all of our work most of the time on a breadboard, like this one. This breadboard is divided into several sections. There are rails on both sides of the breadboard, the red and blue. There are 2 grids, a left and a right grid. There are 5 holes across in the grid, and these rails go up and down. Now, the way they work, this is the negative or ground rail. All of these holes are connected in this direction. This is the positive rail. All of these holes are connected in this direction. So, in the grid itself, they are connected horizontally. So we've got row 1, row 2, row 3, and so on. And on the other side, row 1, row 2, and row 3, the left side of the grid is not connected to the right side of the grid. And a lot of times this break here is used to make assigning these different sides possible. When we put the Arduino Nano on as an example, it goes on over this. The left side of the Nano and the right side of the Nano will connect to these grids, and we'll be picking up the values of the resistors or whatever we need to from that. This is the hardware we're going to be using. 2 wires, an LED, a resistor, and of course the Nano. This is the circuit that I put together real quick. We have pin ground here, which all of these 3 pins pull this ground. It, again, is horizontal here. We then take this and plug it into this negative rail. So all of these holes on this rail here have the exact same ability to be grounded. Anything that we plug into this here, like this resistor, for instance. So we have this connection and this connection into the ground rail. Using conventional flow electronic notation, electricity flows from the positive through our circuit, through the work, which is the LED in this case, through the resistor, which slows down the electricity, and then back into the LED, back into the ground rather here. Now, the way these work, the LED only allows electricity to flow through it in one direction. This is true of any diode. An LED is a light emitting diode. Electricity flows through this in one direction. Had we turned this around so that this leg was plugged into this side and this leg was plugged into this side, this wouldn't light up no matter what we did. This circuit simply would fail. So we have a very specific way to do this. This is called the anode side of the LED. This is called the cathode side of the LED. The cathode is negative. And when you look at the symbol for diode, one leg is straight and one leg is bent slightly. The straight leg is the cathode, the ground or negative rail of the LED. Now that we then go in through this resistor. This resistor is very important in this circuit. What it's doing essentially, this LED does not produce enough load to protect the electronics in the Nano here. If this resistor was not in line, there's a good chance that we'd actually harm the electronics in this device, because there's not enough resistance in this item here to slow down electricity, so it would basically be a short, and we don't want that. We don't want to burn things up. We want to buy them once and keep using them. So we put a resistor in line here. Now the value of this resistor is a 220 ohm resistor, 220k ohms. Most people use either 220k or 330k ohm resistors for this purpose. I'm sure there's a good reason for that, but that's just the two values. I like a little brighter LED, so I use the 220s, less resistance. But again, plenty enough to slow things down. Now, the way I think of electricity, because I think in pictures, electricity is a lot like water. It flows in the direction of least resistance. It has current, like how wide the river or the waterway or the pipe of water would be. It has voltage, which is basically pressure. The more water you are forcing through at any one time is water pressure. The width of the pipe would be the current available. So electricity has current and it has it has current and voltage, and current actually is the word that's used, and then voltage would be the water pressure. A resistor reduces it applies resistance to the pressure, so it reduces the voltage as I understand it. But basically think of a resistor as a narrowing of the pipe you are creating for your electricity to flow through this project. Wherever you see a resistor, you can think of a narrowing of the ability of the electricity to get through that resistor. The higher the value of the resistor, the more resistance, the narrower that becomes until only a trickle of electricity is allowed through. And there are some cases where we're going to be tying hot loads to ground for game controllers, where we'll be using very high value resistors because essentially the positive or the circuit will be made 100% of the time, and there will be a super high value resistor between the two, so that we don't short it. We only pull the full amount of electricity down through the game controller or through the item when the circuit is actually activated. That's called tying a line either high or low. In that case, we'd be tying it low to the negative. However, the way these arrows are going, this is what's called conventional flow notation. We think of electricity as flowing from the positive through the work to the negative or ground, when in reality it goes the other way. There's some screw-ups. Jefferson, who set this all up, really didn't. He understood what he was doing, but he guessed wrong. Essentially, it makes an interesting read if you are curious in the history of this all. But it all started with Jefferson, as I understand it, not being sure what side of his statically charged globes was the negative or some such. Anyway, electricity does flow from negative. Electrons make electricity, and electrons are negatively charged. They flow from the negative of this circuit, from the ground, through the work to the positive, and are returned then to the power source. So even though all the notation we look at like this is the actual schematic, using conventional notation, we see electricity flow out of the positive through the work, see the arrow direction, through the work, and then back to ground, when in reality electricity actually flows from the negative through the work to the positive. It's important to know both, because again, there are times when we're going to be doing some things where we have to put resistors on one side of a switch or the other, and we need to know which side is going to be energized at any one time so that that is positioned properly for different reasons. Now these are both images from Fritzing, which is an open source tool that I use a lot, and as I understand it, a lot of makers use it. This thing it's an awesome tool to depict circuits. This is a very simple circuit. This is our Arduino Nano. This is the ground. Actually, no, this is the TX1. This is pin 1. Energizing these 3 lines. We're carrying it over to this with a wire. We're running through the work. Remember how I said the cathode is the straight leg and the anode is the crooked one? Alright, the way I remember this is the straight leg is the strong leg. If you're standing on the ground, your straight leg is a stronger leg than the leg that's bent, and that's the one you're standing on the ground with. Yay, aren't I clever? So, however you want to remember that, this is the negative, this is the positive. It's important to know them. The positive has a little crooked hitch in it here. When you're looking at an LED, the negative also has a flat space. If we're looking down, straight down at this LED, this side would have a slightly flat side. This side would be very round. They do that as well, so that no matter which way you're looking at this thing, you can really tell what side is which. Resistor to ground. This is the schematic of it. Fritzing will actually even take this and design a breadboard for you. We'll be doing that later as well. Awesome, awesome program. Now, the programming involved in this is really simple. Arduino uses a version of C++. This is a function. This is another function. In every Arduino program, there will be at least two functions. There must be a function called setup and another function called loop. I learned my programming from long ago. Before I get into anywhere, I do all of my housekeeping. We're going to set the control pin variable to the value of 1. We then, in the setup function, we're going to define control pin as an output. That way, in the Arduino land, all of these pins, this pin here could be an output or an input. In other words, this could read a value from something else that could turn on or off, and we want to know whether it's on or off. If that were the case, then I would be setting it up as an input instead of an output. Then we fall through into the loop. We turn the pin on. Electricity flows through the circuit. We wait 1 second. We turn the electricity off. Wait 1 second. And because Arduinos are designed to do things again and again and again, continuously, without being monitored, without being told to do so, the loop function loops. Awesome. So essentially what this does is this turns the circuit on, waits 1 second, turns the circuit off, waits 1 second, turns the circuit on, waits a second, turns it off, waits a second, again and again and again and again. Now the actual coding that's used to do this all is, in the setup we use the pin mode command with control pin as the operand, and we use output as the actual statement. This is going to, now had we set this up on a different pin, we could have used pin 2, pin 20, pin 12, whatever was available. So control pin, output, we're setting pin mode, pin 1 to an output. We drop through the loop, digital write, pin 1, set high, turns on the circuit. We delay 1000 microseconds. The delay command waits a number of microseconds. Had this been 2000, it would be 2 seconds. Had this been 10,000, this would be 10 seconds. Had this been 500, it would be 1/2 of a second. Then we drop through digital write, control pin, pin 1. We set to low. We turn the circuit off. The switch is off, the LED goes off, we wait 1 second. And then it loops, and it loops, and it loops. And this is what it actually looks like when it's working. And that's all there is to it. So, in future videos, Chapter 2 and Chapters 3 of this project, we'll be using this exact same project. Only we'll be doing this with some different programming. The program we're going to use is going to be we're going to set this up as a sine wave. This loop here will be taking degrees, converting them to radians, then pushing that through a sine function in order to produce a sweeping amount that goes up and down, and then we'll be changing essentially the brightness of the pin using a method called pulse code modulation. Just for a moment, think if we turned the pin on and waited for 1 microsecond, 1/1000th of a second, and then turned it off and kept doing that. Well, we're only waiting 1/1000th of a microsecond between turning it on and off. Our eye can't see that fast. We would interpret that as some level of brightness. If we change this so that it were on more often than off, the brightness would increase. And if we kept increasing that, the brightness would continue to increase. If, on the other hand, and this could be done different ways. If we set this at a certain, we left it on for a certain amount of time, and then we changed the amount of time it was off, to some degree we'd interpret that as it being able to be dimmed. Some lighting circuits actually work that way. They turn the light on and off very, very quickly. You can't tell that it's being turned on and off, so you interpret that as a brightness level. Pulse code modulation is a way to do that, and we'll be using a different pin. Pin 1 I don't believe is a pulse code modulation pin. I think it's a digital only pin. In the Arduino world, let's get a close-up of this thing here. Some of these pins, these ones that say A over here, are analog pins. These can read a value from 0 through 255. I believe it's 255. It might be 102.3, 0 to 102.3. And then there are digital pins. Some of these pins are strictly digital, which means on or off. Others are pulse code modulation pins, which can be used, again, to kind of turn things on and off very quickly without having to do it manually through the code. In order to attain various levels of brightness for an LED, or to, actually that's also the method used to turn a servo, make it move left or right. So, hope you enjoyed the video, hope you learned something. Don't be afraid to get yourself one of these things. Go through my videos. I'm going to link on my channel to other people who are doing these videos, who are also teaching other programming classes. There's a lot out there. Just have fun with it. Have a great day.